Hello, pushing on with the 2016 Oxford PAT. We're at question 17 now, is the next one. We've got a diagonal line in the graph below, shows the relationship between force and displacement for a certain frictionless physical system. Right, okay, so immediately when you're seeing this is one of the graphs you should be recognizing. I mean, for force, of course, we can read acceleration as they're proportional to each other, or at least the mass times the acceleration. So here we've got a proportional relationship with a negative thrown in between acceleration and displacement. So we've got SHM. This is one of the graphs that you want to recognize when you get a straight line through the origin like that, negative gradient. So what is it asking? Initially, a mass of 20 grams is placed at a displacement of 5 centimeters and released. What work is done in moving the mass to a displacement of 0 centimeters? So the work done is the average force multiplied by the distance. So we're going to have, what force are we on here? Oh, so we're going up double the force for each centimeter of displacement. So we're going to have 10 average to 5, so we've got 10 over 2 multiplied by 0.05, so that's going to be 5 lots of that, which is 0.25 joules. I mean, area under the graph is another way of putting it. That's the same thing. What is the speed of the mass when it reaches a displacement of 0 centimeters? So what was the mass? We don't. Oh, there we go, 20 grams. I knew it was in here somewhere. So we're going to have that a half mv squared is equal to 0.25. So v squared is going to be 0.5 divided by 0.02. So what is that all in all? Let's get rid of some of these. So we'll have 50 over 2 square rooted. That's just getting rid of these. So we get rid of 2 zeros, top and bottom. 25, v equals 5 meters per second. So that's all good. Describe the mass's motion after it reaches 0 centimeters. Right, well, this is where we can jump in and say, well, it's simple harmonic motion. So what do we know about this? Well, that is going to be our amplitude, because that's what we set it off at. So our amplitude is going to be 5 centimeters. So it'd be useful to say something about the period of the oscillation. So we know that V max is this 5 meters per second. So V max is A omega, and that is equal to 5. And we know that omega is 2 pi divided by t. So we're going to have, what we got on this? So we've got 5 centimeters is our A. So that means that omega is going to be 100, because we've got 5 divided by 0.05. So that's our omega. That is 2 pi over t. So our period is going to be pi divided by 50 seconds. So just going through standard simple harmonic motion stuff, really. But that's the key with this question, and why it's so important to recognize that particular graph. I would say possibly more than any other graph that you study in pre-university physics, it's that one is the one you want to recognize, because it's so easy to miss it. But if you do recognize it, you've got very quick and easy analysis. This third part of the question isn't that straightforward if you don't recognize this as being simple harmonic motion. So make sure you're spotting this one. Really have this as soon as you're seeing that negative through the origin graph, and we've got a force or an acceleration up there versus displacement, then you want to be spotting that immediately. Saves so much trouble. So that's the key to this question, and the key to your revision for these things, and just key to your science understanding all round of spotting SHM when it's there. Right, anyway, stop labouring that point. Let's go on to question 18. We've got a drag force F on a sphere related to the radius of the sphere, the velocity of the sphere, coefficient of viscosity of the fluid the drop is falling through. Right, anyway, so I don't think we're going to necessarily need to understand all of that. K is dimensionless. X, Y, Z are integers. Consider the units, work out the values of X, Y, and Z. Okay, oh, and they've given us the coefficient for viscosity. Right, so let's put all of these in then. So force, so mass times acceleration, so kilogram meter per second squared. That's what we've got on the left. Then on the right, K we can ignore. R is radius, so we've got meters to the power of X. Then we've got this viscosity thing, which they've given us as all of this to the Y. So we're going to have kilograms to the Y, meters to the minus Y, and seconds to the minus Y. And then we've got a velocity to the power of Z. So we'll have meters to the power of Z and seconds to the minus Z. So, right, kilograms is a good one to jump on because we've only got one lot here. So that must mean, so for kilograms, compare those. So Y is equal to 1. That's good. Now we can go to seconds because we're going to have the 2 equals 1 plus Z. So Z is equal to 1. Then we can go to meters and say that 1 is equal to X minus 1 plus 1. All right, so X is equal to 1. So they're all equal to 1. Okay, that was a quick and easy 4 marks. Okay, it's quite a lot to read. And another one of those ones where they're trying to scare you off with words. But yeah, it was pretty straightforward. Light of wavelength 625 nanometers shines onto a metal surface with work function of that. What is the maximum speed of the emitted electrons? They've given us a whole load of numbers here, so that's going to help. They've given us all these constants. So maximum speed is going to be so yeah, for V we got HF goes to half mv squared plus, well, the work constant. That's going to be it, but that's going to be for our V max. So our HF, H, they've given us 6 times 10 to the minus 34. And F, well, of course, that's C over lambda. So 3 times 10 to the 8 divided by our wavelength, which is 625 times 10 to the minus 9. And that is going to be equal to, where's the mass of the electron? So we've got a half times 10 to the minus 30 times V squared plus 1 eV, so 1.6 times 10 to the minus 19. So we need to solve this for V. Right, wonderful. So let's multiply everything by, well, I suppose I could double it. Do I want to try and deal with some of these numbers over here? Yeah, let's maybe deal with some of these numbers over there and get rid of these 10 to the minus 19s as well. So let's multiply everything by 10 to the 19. So we'll get rid of that. We'll make that an 11 and we'll make that a 15. Then of course we've got a 17 here, haven't we? So we can get rid of that and that and that and make it a 10 squared. Right, so that's good. So what are we left with on all of this now? We're going to have 36. I'm multiplying everything by 2 here. So 36, because we've got 6 times 3 times 2, divided by 6.25, which deals with that 100 that we've got there, is going to be 10 to the minus 11 V squared plus 3.2. Right, okay. This is, I can't even remember in this paper if we're allowed to use calculators or not, but let's assume that we're not. So we're going to have on all of this mess, right, we want to try and, I suppose we can multiply this by 4 to get 25s on the bottom. So let's multiply it by 4. So I have to scroll down a bit. So that would be 144 over 25. Then we've got to take off the 3.2. So 3.2 times 25 is 80. So take off 80. And that is 10 to the minus 11 v squared. So that's 64. Oh, excellent. 64 over 25. So 64 over 25, it's nice to have the square numbers, times 10 to the 11 is v squared. So we're going to have to, well, let's take that to 640 and make that a 10, then square root it. So we're going to have 64 times 10, so that's going to be 8 over 5 root 10 times 10 to the 5 is equal to v. That's our meters per second. Yeah, I don't know if we've got calculators or not, but still, that's a nice answer. It's come out with some good numbers. The electrons are then accelerated through a PD of 5 kiloelectron volts towards a fluorescent screen. What is the final speed of the electrons when they hit the screen? Right, well, this is gonna, I would imagine, swamp the velocity we got there, 5 keV for an electron. So we're going to get, so from that, let's just double check this. So our half mv squared is going to be, so that's our 5,000, so keV, we got 1 electron, so we'll be multiplying by that, which means that we're going to have, because m is tiny, so this is why I'm thinking we're going to have a lot here. Let's get rid of that half, which gives us 1, 2, 3, 4 off of there. So that make that a 15. Then we got, so v squared, what did that, m was 10 to the minus 30, wasn't it? Yeah, 10 to the minus 30. So we can make that a plus 15. So we got 1.6 times 10 to the 15. So 16 times 10 to the 14, which is 4 times 10 to the 7. Actually, we'll put it on a separate line because we're on v now. So 4 times 10 to the 7 meters per second, yeah, which is swamping anything that we got from the previous one, where, you know, we're order of magnitude down from that. So yeah, if we're just trying to stick to two significant figures, which is what we're dealing with here, because yeah, I mean, even if we've got, you know, root 10 is just over 3, isn't it? So we've got about 5 times 10 to the 5 there, just, you know, give or take. So yeah, we're going to end up, I suppose we might get up to rounding it to 4.1 on all of this, but still, there you go. I think that's close enough. And that is our, is there anything else in the question? Final speed of electrons when they hit the split, plus the other thing, I mean, that's V max. So we don't know, you know, some of these electrons are just going to be coming out with no velocity at all. So we're going to get, that's going to be our minimum. That's our minimum velocity on hitting the screen, but we might be adding on a little bit more on top. So, you know, we're going to get that sort of order of things, 4 to 4.05 times 10 to the 7 meters per second. So yeah, that was a nice one. We must be getting near to the end of these. I'm going to try and get them all into one video, unlike the last paper, you know, where I just have one left at the end, but it depends how difficult these last couple are. In the resistor network shown below, each rectangle represents a resistor with fixed resistance 12. So these are all 12 ohms. Each circle is a water heater of 6 ohms. Each water heater contains 1 kilogram of water at 20 degrees C. All right, so all of the power dissipated by the water heater heats the water. Okay. 84 volts is applied as indicated in the figure. Right, how long does it take for each individual water heater to raise their waters up to 27 degrees? Right, so we've got a delta T of 7 degrees C. They've given the heat capacity. So what's going, let's have a look at our setup here. Well, everything's symmetrical on this. So A is never going to heat up because there's no potential difference across it. And the reason we can say that is these two resistors at the top are identical. So they're going to split the PD equally. So they're both going to have 42 volts over them, same as the two water heaters B and C. They're both going to have 42 volts over them. So by the time we've got here, that's 42 volts, that's 42 volts. There's no potential difference. So we can say A will never heat up So that's one thing. Then we can say, so B and C, B is equal to C, and they both got 42 volts. So the power is going to be V squared over R, which is 42 squared over 6, which is, so that's 42, which is 6 times 7. So we'll have 42 times 7, which is, what's 42 times 7? That's going to be 294 watts. So that's what we got happening there. So our 7-degree rise for, what was it, 1 kilogram of water. So that means 4200, that's our specific heat capacity, times 7, because we've only got 1 kilogram. So that's the amount of energy that we need. And then we need to divide that by 42 times 7, which is our power. I've put it back into 42 by 7 because we can see why they've picked 84 volts, so that it cancels nicely. So the 7s are going to cancel, the 42s are going to cancel, and that's going to leave us with 100 seconds. Obviously, lay this out better. Don't just dot stuff all over the page like this. You're going to want to turn it into something which, you know, fits more nicely on the page than me trying to squeeze this on the screen. But this is more to demonstrate the process that you're going through in a very quick 8 marks for that question. There's not really much to say about that. There isn't anything conceptually awkward about it. Right, I think this is the last question, 21. Yes, it is. So, right, well, it's only 6 marks, so it can't be that bad. Sphere of radius 2 meters, made of a material with the same refractive index as a vacuum. Interesting. So we got n equals 1 in there. Supported in a fluid, refractive index n on the outside. So they reversed what we normally have by a straight wire going through the centre C. Laser directed towards the sphere, going parallel to the wire, offset by 1 meter. Okay, wonderful. Strikes a, what refracted index n would be needed for a refracted beam to travel at 45 degrees relative to the line AC. Right, so that's all. Well, that is our normal, so that's good. 45 degrees, because it's going to bend away from the normal now, because we're going into lower refractive index. So we want 45 degrees there. So we've got the, what have we got? The n side. This is our theta I. What refractive index, isn't it? Right. So anyway, let's put theta I there. So n sine theta I is going to be equal to, well, n is 1 here, so leave that bit out. Sine 45 degrees. Right. So that's fine. We've got 2 unknowns here, which is what's bothering me. Well, we haven't used any of the dimensions of all of this, so we're going to, yes. So this is going to give us, that's theta I, isn't it? Because all of this is, we've got 2 parallel lines, that and that are parallel. So that's 1 meter, that's a radius, which is 2. So sine theta I is going to be opposite over hypotenuse, which is a half. So n over 2 equals root 2 over 2. So n is equal to root 2. Right, okay, that was good. Another beam, not necessarily parallel with the wire, strikes the sphere at point A. Right, so it's hitting in the same place, but we're changing the direction of the beam. At what angle relative to the line AC should the beam be directed so that it would be completely reflected by the sphere? So we want our, we need to find our critical angle and then say that theta I is going to be greater than that. So we want theta I to be greater than theta C, where, so for theta C, we've got the n, which we've got is root 2, sine theta C has got to be equal to n, which is 1, times sine 90, which is 1. So that's got to be equal to 1. So theta C is going to be inverse sine 1 over root 2, so that's 45 degrees. So we're going to get total internal reflection when the angle of incidence is greater than 45 degrees. Right, that was a quick finish on that one. Once you get used to the fact that they've changed the usual setup, I mean, it doesn't matter that this is a sphere that we've got here. We've still just got a normal going on at the point where it hits, where the beam hits the sphere. So that hasn't changed anything. But once we've got used to the idea that we're refracting in the opposite direction to what we're usually dealing with, and then spot that geometrical property that they've given us. But as soon as you get stuck on something like that, thinking, oh yeah, we've got two unknowns in one equation, well, there must be something else in the question. We had that 1 meter thing here, which we hadn't used. I mean, they put them in the pictures, the 1 meter, 2 meters. So if you got information that you haven't used, well, it must be something to do with that. They don't tend to hand out, although occasionally they do, but usually they don't give out information that they don't expect you to use. So that brings us to the end of 2016, Pat. Not a bad paper. It had a couple of sneaky ones, I suppose, in the physics. That one with a charge sitting between the two positive charges, that was a bit annoying. But by and large, they were a nice bunch of questions. It was a nice paper, this one. So I'll be back for 2017 in the next video.